Great, thanks. Okay, it's my pleasure to introduce Jiayin Dong, DJ, to Gemini. We just did an observing run, I think Sunday night on the summit with IRTF, looking at some really bright stars in planet transit. So I know DJ way back when I first entered grad school, we both attended a conference together. So DJ did her undergrad at University of Illinois, Urbana-Champaign. Then she moved on to doing a PhD at Penn State with Becky Dowson. And then she went to New York City, Flatiron Institute. And then this coming fall, she'll be returning to her undergraduate institution as an assistant professor. And so today she will be telling us something about initial conditions of multiplanetary system with simulation-based inferences. So DJ is one of these rare experts whose expertise spans from simulation, statistics, and also observation. So today, I'm all excited to hear what you have. Awesome.
Yeah, thanks so much, Sarah. And just thanks you for the invitation, the RTF observation, and also like the opportunity of being here. Until very recently, I mean, like this Sunday, I just realized how spoiled I've been on all the observations. All I've been doing in the past, submitting my target list onto a queue. The second day, I got the reduced data. Never realized all the hard work being done by all the observers, instrumentalists. Is really a unique experience for me to go up to Mauna Kea and experience everything. And then I'll learn to appreciate and taking care of my data much more carefully. So today I will be talking about the initial condition of multi-planet systems. How can we infer that with simulation-based inference? My background is mostly in exoplanet formation, dynamics, demographics. And I know lots of the audience here is now like working in this field. So please feel free to interact me if you have any questions. And I'm happy to discuss, like since in a lot more details, we don't have to go through like all the slides I prepared. Okay, so let's get started. So I'm doing lots of exoplanet observations, and the data we get, what we realize is the systems we observed are actually involved systems. So what I mean by that is we look at these observations and we see evidence of exoplanetary system evolutions, particularly on a dynamical perspective. I'm showing the most extraordinary example we ever had is the TRAPPIST-1 system, which is a system hosts 7 small planets and in a resonant chain. So you may heard of resonant pair is 2 planets that has their orbital period ratio close to some certain integer numbers like 2 to 1, 3 to 2, and their resonant angle is vibrating at a certain angle. A resonant chain is more than that. You see 3 bodies, 4 bodies, 5 bodies. In this extraordinary example, 7 bodies. And every 3 of them, they have the resonant angle, 3-body angle vibrating. Some of them have 4 angles vibrating, even 5. It's really a compact, well-organized resonance system. Every planet's orbit goes through certain angles so that they are coordinating with each other. You see people like making really nice music on TRAPPIST-1 system because of the well-resonating resonant of the system. So here you can see the transit like curves of the planet, and little dips are each color presents a certain planet. You can see the fist-folded ones and can see how their orbit align. So why TRAPPIST-1 is extraordinary for us, it's not just, how well organized the system is, but it's actually a clear evidence of convergent disk migration. To get system to such a nicely organized compact architecture, we need some source of energy dissipation. We need to have the system to remain stable. And the main proposed theory for this is, okay, there is dynamical interaction, there is dynamic evolution happened to this problem before, which is a convergent disk migration. And in more recent years, there are more examples of resonant chains discovered by the Transiting Exoplanet Satellite, which is shortened for TESS. And what TESS is good at is detecting bright systems. I'm showing you one very exciting test systems being discovered recently by Fei Dai from U Hawaii IFA in Honolulu. And this is TOI 1136, which is a 6-planet resonant chain. And you can see the purity ratio of those 6 planets. Most of them are first order, which means the purity ratio number is different by 1. So 3 to 2, 2 to 1, 3 to 2, 3 to 2. And there's a pair like that has the second order resonance, like 7 to 5. Since the systems are discovered by TESS, their host star are bright. It means we can do ground-based follow-up. Fei did a Rutherford-McLaughlin effect measurements on planet D. So you do the Rutherford-McLaughlin effect observation when the planet transiting in front of the star, and you use a high-resolution spectrograph. For example, like Muon X, HARP Moors, all sorts of instruments that are possible, like KPF on KEC. You can get the radial velocity at high position, and so basically here, when the velocity is non-zero, this is when the planet transit. And since the star itself is rotating, one side of star is blue shifted, the other red shifted. And when the planet block one side of the star, the integrated radial velocity could either be positive or negative. So when we read this signal, we look at whether the signal is symmetric or not. In this case, it's very much symmetric. It means the planet's transit is well aligned. So vertically, so for example, here is a stellar spin. The orbit must be well aligned with the spin axis so that the planet cross the stellar disk horizontally. So this is why the signal is symmetric, and this is probably one of the very first resonant chain system that we show that they are not just like architecturally compact, well organized, their spin orbit angle. The whole system is actually well aligned with stellar spin. We can do more. We are in the TESS era. The systems are bright. This is probably the first resonant chain system, HD 110067, that each of the planet we have a mass measurement. So also benefit from the really high resolution radial velocity we can get. And also we have a better treatment on the stellar activity using a Gaussian process. Each of the planet in the system has a mass measurement, and we can study, since we know the radius, we now know the mass, we can study, okay, the density variation of the planets in the same system in a resonant chain. So those are 3 resonant chain examples. All I want to argue here is those systems are dynamically involved. Some certain mechanisms drive and it's like the migration.
A question.
Yeah.
How common are these resonant chain planets just
Right.
out of the entire population?
Yeah, that's a great question. I think the status number roughly 5%, so it's very much a small population. And that leads to the next point. That's a great question, by the way. That leads to the next point. When we compare to the majority of the small planet, what I mean by here is like super Earths, like small planets, smaller than 4 Earth radii. Those are called super Earths. So the majority of the super Earth population we observe are not in this compact resonant chain setup. The most prelim theory we have for now is called the breaking the chain. So we believe that the systems are for a resonant chain at the beginning, but the disk, which is a main driver of the system migration and stability, get dissipated. And then, okay, the chain is broken. So you can see here is very complicated plot by Isidoro 2021, who proposed this whole break the chain theory. And you see, okay, the system was compact and some disturbation happened after the dissipated. You end up with still a multi-planet system, but they're no longer in this resonant chain setup. So with this model, we can explain most of the observation of the super Earths. Okay, so dynamic evolution happened on small planets like rocky planets. It also true on those giant ones. Hot Jupiters, those are Jupiter mass planets that with orbital periods of only a few days. And using the RM effects, Rotherham clocking effect measurement technique I talked about earlier, we can measure the stellar spin orbit angle or the projected obliquity on large population of the hot Jupiters. And what we found quite interesting is that the majority of hot Jupiters around hot stars are misaligned, and their spin orbit angle is broadly distributed. There is still like a preference of zero, which is like spin orbit alignment, like nicely organized. But in many of the cases, the spin axis, the orbital axis of the Jupiter is actually misaligned from the stellar spin axis, and actually follows the isotropy distribution. So the reason for that is we don't think like it can be described purely primordial. It likely suggests the hot Jupiter system, when they form, there's some really chaotic dynamic hot mechanism happened on the hot Jupiter formation. And high eccentricity type migration is one of the proposal, which is this hot Jupiters actually begin quite far from their host star, and there's some really dynamic chaotic interaction happen, excite the Jupiter's eccentricity to some really high value, and then it's gradually circularized. So when the eccentricity was excited to the really high value, the mutual inclination also excited. And once the planet gets circularized, its spin orbit angle may not be totally washed yet. That's why we observe this really broad range of stellar obliquities. And we do have evidence of this how Jupiters undergo this high immigration. I'm showing two discoveries. The left one is TOI 3362b. It's an 18-day orbit planet that has an eccentricity of 0.8. That's why you see the radial velocity signal is such extreme. That is because of the high eccentricity planet. And I was very lucky to discover this planet when I was in grad school. And this observation was done on the 1.5 meter Charon in the southern hemisphere. It's quite exciting using such a small telescope to make discovery on such a planet. And it's mostly because it's super eccentric, the signal is large. And on the right is another TIC system, test system that is labeled by TIC. Is discovered by my colleague Arvind Gupta. And the orbital period of this one is much longer, but also its eccentricity is much more extreme. So this one is, I forgot the exact value, but orbital period of longer than 100 days and eccentricity greater than 0.9. That's why you see these extreme peaks. So those are examples that we start discovering this task that showing we actually know this proto-hot Jupiters, those hot Jupiters still undergoing high migration. It's again, it's an indication that the exoplanet systems we observed are dynamically involved. I recently observed it has some like dynamical imprints on it already. And we know the planetary systems are dynamically involved actually a long time ago. So here I'm now showing you all the co-Jupiters. We know this population, actually a statistic of this population nearly 20 years ago. So those are the first round of radial velocity observation we've done on the very first population of exoplanet we discovered. So Paul Butler's survey on the exoplanets around nearby stars. So you see this distribution of eccentricity versus major axis. The majority of them are Jupiter-like planet. And you see, okay, especially when you go to the large major axis beyond 1 AU, what we call co-Jupiters, the eccentricity is actually quite broad. And similarly, Jason Wright showed this dynamically involved co-Jupiter population. So with all this I've been talking about, the point I want to reach is systems to be observed. We have really nice observations. We have lots of multi-axis of observations. But we know the systems we observe, they are full of dynamical imprints. From a series or like a planet formation perspective, we are really interested in what is the initial condition the systems are coming from. That will be a really important information for us to build a planet formation model. And also we care about what is a driven physical mechanism that shapes the observation trend we observe nowadays. So lots of observation evidence, lots of observation constraint we have. We want to trace back to the initial condition of planetary systems. And that's a problem that we've been trying to solve quite long since we discovered the hot Jupiters. We want to trace back, what sort of setup for planetary system setup forms hot Jupiters? What sort of planetary system setup we begin with to form those resonant chains, to form the majority of super Earths, to form the majority of giant planets. So that's the question I want to talk about today. And to solve this problem, we are actually under some quite constrained assumption. When we observe an individual planetary system, when we observe a single hot Jupiter, okay, it's a really unique system. But it doesn't tell us that much. When we observe a population of hot Jupiters, we now know, okay, this might be some characteristic property of hot Jupiters. And we can describe this, collecting all the hot Jupiters observation we have and describe them into certain statistics. But there's an underlying assumption, which is the exoplanetary systems, or for certain type of planets, the systems are independently and identically distributed. So this is more of a statistical statement, and we need to leave under this before we can further move on to infer the initial condition, or even just to infer the population level properties of a certain type of planet. Okay, so that's the goal of this work, determine the initial condition. And I want to first talk about a few really promising perspective of doing that allow us to do this. First, if we think of the those dynamical imprints I talked about, those are all driven by dynamics, which means we can simulate them with embodied simulations. So that means, okay, at least it's doable. We know the sort of understand the physical process, and we can describe them with the modern embodied integrators. And okay, we have all the dynamical imprints, we have the observations, really rich observations. We know the planet's period, planet size, planet mass. Some of them we have really precise constraint on the eccentricity, on the spin orbit angle. So we have all of those rich information from observation. So another really helpful thing for us to do the inference. And then it's straightforward. Okay, all we need to do is, we begin with some theory. We involve the system with embodied simulation. We match that with the observation. So there is really promising perspectives like, okay, we can do this. We have all the tools we need to do this. But is that really the case? I want to talk about a few more challenges. First, there is a large parameter space to explore. We want to describe the initial condition. And this initial condition is actually quite spacious in terms of the parameter of interest. The multiplicity, the spacing between the planet pairs, what is the planet masses, what's their initial eccentricity inclination, some small but non-zero values. So that's like the large parameter space we need to explore that sort of limit us to do the inference. And also we have a high dimensional data to match. That's when actually you may think, observation is great, right? It gives us all the different perspectives. But also it means, we have the challenge. We need one certain theory to match all the observations, and it turns out to be pretty challenging. So we want to match this high dimensional data, mass eccentricity, spin orbit angle, semi-major axis, all sort of observed values. We want a theory that is good enough to match all of those. And okay, the mentioned many times, the system we observe are dynamically involved, and most of them are actually giga-year timescale. So to simulate each of them, it actually has some certain computational cost, expensive to simulate. And lastly, I have to talk about the observation bias. As a sort of an observer, I shouldn't call myself observer in this room. I know biases when we even start writing the proposal, right? Only the brightest targets, the quiet stars, are being selected to do certain observations. Or for the Rossby-McLaughlin effect, it's the opposite. Only the high V-sun-I fast spin stars are being selected to the observations. So there are all these sort of observation biases we have that need to be taken into account when we compare our prediction to the observations. Okay, so that's the main limitation. That's why, like in our field, we know those extraordinary planetary systems. We can describe them, resident super Earths, hot Jupiters, warm Jupiters, cold Jupiters. We can describe them, but we don't have a good theory to see, okay, where do they begin with, and what mechanisms drive their evolution. It's more of the computational costs and not a good way to directly match the predictions observations. So I want to introduce a new approach. It's called simulation-based inference. And our goal is to use this approach to overcome the challenges I talked about earlier, the computational cost, the high dimensional parameter space, that we need to explore about those initial condition parameters, and also the high dimensional parameter space of the data, the observation data we have. Okay, so let's go through the simulation-based inference technique. You may have heard of this name, or some of its more popular previous names. In the past, it's been called the approximate Bayesian computation, or the likelihood-free inferences. I think the likelihood-free inference was used more popularly in, at least in exoplanet or cosmology in the past. Now it's all been updated with this fancy name, simulation-based inference, SBI. So, okay, we are still living in this Bayesian regime. We have a parameter of interest, which is theta. We have some previous beliefs. We have some priority. We assume some prior distribution on this theta. And we have some observations, which is theta d. That's our likelihood, the data conditioned on the parameter theta. And we have the posterior, the theta parameter of interest condition or given the observation. So this is the Bayesian equation and Bayesian theorem. And we usually, in the past, we have some prior beliefs, and we can write down our likelihood. We run our MCMC to find approximation of the posterior. So that's the more standard approach that we use to model lots of the data. And in this simulation-based inference framework, this likelihood part is usually undescribable. Or it could be like, oh, it's too expensive to evaluate the likelihood, or it's just impossible to track the likelihood. There are all different possibilities. We don't directly write down the likelihood. So instead of writing down the likelihood given the prior, we approximate the posterior, or doing the MCMC on the posterior. It uses a distance function. And some summary statistics. So we can describe our observation with certain summary statistics. And given each theta, we derive a summary statistics. We compare that to the observed summary statistics. We calculate the distance between the two and accept the sample when it's below a certain tolerance. So my first read this, I feel a little bit abstract, and I found this pretty nice demonstration on Wikipedia, and we can go through this. I think it's going to be quite helpful. So see, we have some observed data, and here's 1D, and we describe it into some summary statistics. Here is a mu. Okay, so we have this observation. We are interested in the mu, and we want to no, we have this observation. We summarize this into some certain mu. We have a parameter of interest, which is theta. Okay, let's see. Okay, we don't know too much about this theta. We see, okay, it's just uniformly distributed from certain values. And then we draw a random value, draw a random theta out of this distribution. We run the simulation and find the summary statistics. So we for each theta, we get a summary statistics, mu1, mu2, mu3, mu_n. So we can do many draws. And now we look at this mu, we compare that to the observed mu. If these two are close to each other, we accept the sample. If these two are not that close to each other, we reject sample. And that is all described by this tolerance epsilon that we define. So in theory, if we have a good enough summary statistics, and if the tolerance is absolutely small, then the posterior we derived, or like all the samples we accepted by the end, should exactly describe the distribution, the posterior distribution. But this could be quite hard. Like if we set the tolerance to 0, like each data point perfectly match the observation, then it takes forever long for us to simulate this. And the summary statistics, okay, we could now like input everything into the summary statistics. Basically, we have to describe it into certain ways. So that's our classical approach, and you can see it includes lots of computing power. Basically, we need to inject, decide to accept the sample or not accept the sample. We need to run this many times, and by the end we have approximation. And okay, so
DJ, quick question, please. The whole time is it being drawn from a flat distribution from the prior? Okay.
Yeah. So it could be a flat distribution, or it could be a certain distribution. That's your.
I see. It could be an arbitrary.
Yeah. That's your
Yeah.
belief of your prior. You want to draw from certain prior distribution.
Oh, okay.
Yeah.
Okay, thank you.
I have a follow-up question. Maybe you'll mention this later. How large of a effect does the distance measurement, in essence, if you're trying to compare point to point, or you can try to compare it in a probabilistic way, how does that, how does that affect the outcome of the posterior?
Right. Yeah. So anytime when epsilon is non-zero, it means the posterior we get will be slightly broader than the true posterior. Since when the observation, when the sample is selected is perfectly matching the observation, then okay, the tolerance is 0. But like when the tolerance is non-zero, then okay, we know that for sure the posterior is going to be slightly broader, but that's okay. Since for us, like making a slightly worse but robust inference is better than having a really small uncertainty but incorrect inference. The firmer one is much better, right?
So you would want to prefer distance measurement in which you get a broader posterior? Is that what you're saying? Instead of having a very narrow posterior.
I mean, like, we know this method is not going to be perfect, that's the point, but we want the epsilon to be as small as possible. So that we can get a as close posterior as possible. But we also know that, okay, if we put epsilon really small, then it's gonna take even more sampling to actually get a effective posterior distribution. So it's a balance between the two. But whenever we get the posterior, at least we know that we are not underestimated.
Okay, well, we can discuss.
Yeah, yeah. So, okay, that's the, is there a question? No, okay. Yeah, so that's the more of less classic Bayesian approach, and we can just simplify it into a diagram. This is by a really nice review by Miles Kramer on all the SBI techniques. And this is the most like classic model we've ever had. Prior, make a proposal, do the simulation, getting the summary statistics. This here is like each single one is like X prime. We compare to the data, the summary statistics of the data, which is X. We decide to reject or accept, and eventually we get the posterior distribution. So it's pretty nice rejection sampling in a sense that we get the posterior when we couldn't write down the likelihood. But you also see the problem here, as what Cesar mentioned. We need to deal with, okay, epsilon is non-zero. We need to deal with when epsilon is small, we need to run lots more. Each simulation is expensive. To get a robust sampling on the posterior, it's just really expensive for us to do this. And that's the reason why this technique exists, but it hasn't really been well applied in astronomy, at least in the last 2-3 decades even. So this technique has been there at least since 80s. I don't recall the very first beginning of the when at the beginning of when it was proposed. So, okay, yeah, it's a great technique when we don't know that much about the likelihood, but it's expensive. What being proposed more recently, what I call the modern SBI, is a network that is powered by, it's a framework that is powered by neural network. So you know neural networks, its ability of learning patterns, that's what's good at, like given an A, given a B, like what is a pattern that linking between A and B, that's really good at dealing with. And it's sort of our problem here as well. So for this modern SBI, instead of using the rejection sampling to calculate the whole posterior, it can directly learn this posterior distribution from a training set, which is the theta and data pairs. So we still run simulations, but now we can run it in with much small number of sites. So given each theta and data pair, what it's trying to do is to learn a posterior density that is trying to maximize this log posterior density out of this training set. So that's all it's trying to do. I gave, again, I have some theta, and for each theta, I derive some certain summary statistic D, and I have many pairs of those. I feed that into a neural network and let it to tell me what is this posterior density distribution would be like. And I condition that onto the real observation that gave me the posterior distribution. We can see the same thing in this framework again. Prior, make proposals, and from the theta pairs, I run the simulations. So now all I need to do is to make sure the here the theta, the parameter space we are interested in is well covered in those simulation set. So for example, if my prior is uniform, I probably need if it's one-dimensional uniform, I probably need something like 30 data points to well describe the distribution. If it's like multimodal, then I probably need some more number. So all I need is, okay, I have the theta that is valid that could sort of probably the prior. And for each theta, I do the simulation. And I use this neural network to find the approximate posterior conditions as posterior density estimator on the observed data, and then I get the true posterior. So that's how the modern simulation-based inference work, and it actually requires much less number of simulation sets. Instead of running one, if we don't like it, we reject it. We can use all the information. We can use all the simulation sets and put that to actually to the approximate posterior and eventually infer our posterior that we are interested in. Okay, so the goal, go back to exoplanet, go back to inference the initial conditions. The goal is to apply this framework onto the inference of the architecture that form warm drifters. I didn't describe warm drifters very carefully. I talk about hot drifters and cold drifters. Warm drifters is actually my really research lab. I've been doing warm drifter works in the last 5 years. And those are giant planets with warp periods of 10 to roughly a few hundred days. Giant planets still, they are somewhat unique compared to hot drifters in a sense. They have larger warp periods, and also it means larger planet-star separation. So less tidal effects. Hot drifters, their eccentricity are all there close to zero because their orbits getting tidally circularized. So eccentricity is important information that has been washed out from the hot drifters. Warm drifters instead, large separation with her tidal effect. The eccentricity is preserved. Also, the spin orbit angle, the stellar obliquity, we measure of the Rossum-McLaughlin effect. Those are very important dynamic imprints that are preserved on warm drifters that we can use to infer their initial conditions. And also there's a growing sample. Mentioned TESS many times. TESS is giving it's observing like planets around bright stars, and we can characterize their properties. And that is specifically beneficial on these warm drifters. In the past, we do have discoveries out of Kepler, but their hosts are too faint. We couldn't really do detailed characterization. The ground-based exoplanet detection are very much limited to even shorter period planets. So the bright warm drifter sample was expanded a lot in the last few years benefiting from TESS, and we have the characterization of them with all the ground-based facilities. All the way from validation with small telescopes such as LCOJT to the Raycon spectroscopy like Charon, Minerva, Australia's, and to the characterization. Most of the work I've been doing is made by Vin Newit, which is high resolution spectrograph, KPNO. So, okay, a lot more data. That's also exciting. And also with those new data, we actually see some very interesting dynamical patterns that we don't know before. Let me see a few words about that. So TESS gave us a large sample of warm drifters. And back in 2021, I modeled their eccentricity distribution. And what is quite interesting is that these warm drifters are actually showing a bimodal eccentricity distribution. So in the past, we thought, oh, warm drifters must be like those cold drifters, has a very broad eccentricity distribution. But instead, we also find, okay, the eccentricity is broad. But we actually find that there is evidence of two components, a rather low eccentricity component and a more high eccentricity component. And it's been a little bit puzzling on how to explain this bimodality. Whether warm drifters has multiple origin channels that form this bimodality, or could a simple single mechanism form the bimodality. This is back in 2021, shortly after TESS launched, and we got the first population of worm Jupiters. In later years, many of these worm Jupiters are being followed up with radial velocity. So we have understanding on new dimension, which is a planet mass. The most straightforward dimension that we get out of the radial velocity follow-up, but turns out quite helpful. So now those are the worm Jupiter population. On the vertical axis is the planet mass, and on the x-axis is the eccentricity. So you see, if we actually push this down in terms of eccentricity distribution, it's still bimodal. You see a low eccentricity population somewhere clustered here, and then you see a high eccentricity population, and then we see this mass dependent. It's actually low mass worm Jupiters tends to have low eccentricities, and high mass worm Jupiters tends to have high eccentricities. So that is quite interesting. And we look back into the literature. So this was discovered by my colleague Arvind Gupta last year. When we saw this trend, we looked back into the literature and found, there might be a similar trend in cold Jupiter as well. This is not like something unique to worm Jupiters. And for this trend, it's actually best explained, or our best hypothesis theory is planet-planet interaction. So you may think of, low mass planets, they are more likely to get scattered away. So if they have giant planets nearby, then only the low eccentricity ones can survive. So low mass, high E ones are more likely to get scattered. So that's a survival bias we observe here. And then planet has some typical masses. What I mean by that is, there's certain, if we have a group of planets with similar masses, they're most efficiently to scatter each other and sculpt a rather broad eccentricity distribution. So this is just a very general, probably even not like theoretical description, not robust at all, way of describing these observations. It's just a first read out of the data. And because of those interesting patterns, that motivates us to better understand the physical mechanisms or the sort of architectures that leads to this evolved population. So what we do is run n-body simulations and use this try to match the mass eccentricity distribution of worm Jupiters. And see, here is a parameter space that we are interested in. It's also our prior. We have we consider the planet systems. Here's a M total, which is the total planetary system mass from 0.2 to 20 Jupiter masses, like spreading 2 order magnitude. We consider the separation between the planet pairs between 3 to 5 mutual hero radii. And 3 means really compact, chaotic, unstable systems. And 5 is more of, likely to be stable systems. To give you a sense of this value, in the solar system, we are thinking of something like 10, 50 mutual hero radii. So what we are simulating here is actually quite compact. And the reason for that is we know the worm Jupiter systems are quite eccentric. To describe that population, we are thinking more towards a compact system. And another thing we could do is to describe the variance of the planet mass in the same system. So we have the M total, and M total divided by the number of planet, we get the mean planet mass, and then we can describe a variance of that. So it's like 0 means, they all have the same masses, and 0.5 means they have very different masses. And each system in this setup, we just assume 4 planets. And we put the innermost one at 0.1. This is our worm Jupiter. We involve the system for, I should put 100, I miss a 0 here, 100 million years. And initial setup, the eccentricity and inclination are quite low, and all the planets are randomly oriented. So we run 10,000 simulations with rebound trees, which is a hybrid integrator written by Tiger Lu. It's very recent. And TRIS is very fast, robust on population level. So we can complete this 10,000 simulations less than a weekend. So that makes the simulation very much doable. Okay, so with this said, we can apply that to the simulation-based inference framework. But let's first take a look at what are the some parameters we are interested in and what the data tells us. So here is 2D on the horizontal in the horizontal direction, I gradually increase the total masses of the system, and vertically gradually increasing the separation of the planet pairs between planet pairs. So in each of the panels, the vertical axis is eccentricity, the horizontal is the warm Jupiter. The warm Jupiter is eccentricity and the warm Jupiter mass. So out of the simulation, I already do the observation bias to identify the planet that is most likely to be detected by the transit. So that's like one layer that we already take count of the observation bias. And you can see, okay, for compact systems, as the total mass of the system increases, okay, the warm Jupiter mass also increases. That's kind of understandable. And vertically, if you see, okay, let's see this row, as the separation, this is the most broad separation set we have. The majority of the points actually cluster like eccentricity close to 0. And as the separation gradually decreasing, we see, okay, there are less 0 eccentricity planet, but the majority of them have a broader eccentricity distribution. So this is the subset of the simulation that we do see, okay, there are some certain trends in the data, which means that, okay, it's actually trackable out of the mass eccentricity distribution on those initial parameters, initial architecture parameters that we care about. And now same plot I'm putting into the warm Jupiter observation we have. So I'm only using a subset of the warm Jupiter samples, because in the simulation I put the innermost warm Jupiter was 0.1 AU. And in our observation, the warm Jupiter has larger semi-major axis, and they're actually a dependence of the eccentricity on the semi-major axis. So if I put that in, that should be another axis, and that is not yet in this simulation set. Okay, so with that, for the subset of the warm Jupiters labeled in those orange dots, you can have a sense on what parameter space is most preferred. Very unlikely to have really low mass systems. Those are systems with masses like between 0.2 to 0.5 Earth masses. Those are unlikely, or even to 1.3 Earth masses. The simulated data dot are just like too low mass compared to the observed ones. And it's also unlikely to have the really high total mass systems, because like our observation having lower mass than those. So we know like some sort of preferred parameter space on masses somewhere between this 1.3 to 8, even slightly lower than the 8. That's the total mass range that if we infer that means our model making sense, right? We have a sense on this observation or compared to these predictions. And now we can look at the separation, and that is a little bit tricky, since if you look at, for example, the middle column, it has a preferred mass range where like you look at the separations, their eccentricity distribution doesn't really matter that much. There are some minor trends like on the mass eccentricity space. That's like the trend that's mentioned about there might be like a positive correlation that is seen in the simulation that set slightly, but not that well. That's the thing, like, oh, that's the limitation of us. In the model, especially this neural network, is able to find all the in complicated implicit trend that written into the data. We are now required to getting this just out this have our best educated guess on what it might be. We can look at this, having a sense on what might be the preferred parameters, and understanding our result, whether our result is robust or not. We will leave the neural network to do all this complicated implicit work. Okay, go back to the inference framework again before I show the result. So we are interested in the total planet mass and separation. We described them prior as uniform prior, log uniform for M total from 0.2 to 20 Jupiter masses, and separations 3 to 5 neutral Hill radii. And out of this, we generate many data sets with our unbounded simulations to describe, okay, given a certain M total and theta, what is the mass distribution is. And we feed 3,000 samples of those, describe their summary statistics, and let the neural network learn the posterior density. We conjunct this onto our observed mass distribution and getting the posterior. Okay. So let me show you what we have. I put preliminary here since I don't want to overclaim this. This whole technique is quite new, novel, and the robustness of the simulation-based inference. More specifically, the neural network is always under discussion. So I would put preliminary here. But here's our inference. The horizontal direction is the mutual separation, the vertical is the total mass. And here it's in the log scale, so we need to do the exponential of that. You see the inference is quite nice. The shape is good. We get a separation of 0.3, 4.3 mutual Hill radii, which is compact, but not that compact. Much more compact than our own solar system, but not as chaotic as what we thought. And the total mass is 0.94. You do the exponential, you get something like 2.6 Jupiter masses. So that is quite exciting inference result. We now know some sort of initial architecture of this warm Jupiter systems before they dynamically evolved. And we can use this to inform the formation theory, the giant planet formation theory, use that, see, okay, if there's a model from the formation perspective that can match this initial state. So how do we know if this inference is robust or not? What we can do is we have a separate set of simulations that have never been seen by the model. We use that for the valuation. And for each of that, of this validation data set, we know the true value of the theta and M total. We can apply this model to do the inference and check, okay, where the inference is and where the true value is. And we do that a few thousand times and derive, okay, how likely are our model to be able to correctly predict the true underlying hyperparameters that they are interested in. So that's what I'm showing here is a model validation. For a perfect model, we expect everything to line up to this one-on-one line. Our model is not perfect, but it's not that bad. It's not like something like this, right? It's close to this one-to-one line. So for each of the data points, I checking, okay, here is, here's our 50% posterior credible interval. And how often does the inferred value lies into this 50% interior? Theoretically, we should have 50% chance of the data points lie into that. And that's here you see, okay, what we truly get, we get something like 42% in this case. So our model is like, okay, not too bad in a sense. It not as good as the it's not perfect, but it's giving somewhat reasonable inference on what is a true parameter spaces. Okay, for the last few minutes, I want to talk about some caveats. Those are the problems I'm thinking of the whole time while I'm working on this project. How robust is the summary statistics? I didn't describe them into great detail. In this case, we want to model the mass eccentricity space of worm Jupiters, but we only have this many observations, each have some certain uncertainty. All I do is to do a 2D histogram and use that as the summary statistics. Whether that is the best way or not, that's something to discuss. And how well our observation and uncertainty handled, we can do some weighting into this histogram, but we are limited by small numbers. It's all sort of engineering and that we couldn't really fully have them handled. And also like the question that scared me the most, I've been thinking this the whole time. The simulations we have, is the simulation pool we have good enough to cover the complexity of the universe? That's the biggest question. That's the question I'm worried the most. Are we actually describing all the parameters like semi-major eccentricity? The semi-major axis is something we know that we are limited. We only have the 0.1 AU as the innermost planet, which is not always true for worm Jupiters. And multiplicity, we only have 4. So that's 2 very obvious limitations, but there could be more. We consider the planet interaction as the most dominant effect. What if there are other impacts that we never think of? So those are like questions we have and we need to keep in mind when we interpret those looking very nice results. But still it's very promising. We, for the first time, have the estimation of the initial condition instead of some just, we have some inference, which means, we can quantify the uncertainty instead of a point estimation, something that is really hard to interpret. Okay, so I will just leave the summary here. The most important parts, let me pick one of the 3. Okay, the first one, simulation-based inference. This is a novel approach, and if you have something you can simulate, and if you have parameter that you're interested in, you use that to simulate some result to match the observation. You're likely to be able to apply this framework, and the benefit is easy to use, just a small set of simulations. You can do this already. Lots of exoplanet applications that can be used on this with this framework. A lot more exciting works. I think it will come in the next few years.
Thank you, DJ, for a very nice talk. Let's start with questions online, and then go to the room. Do we have any questions online? Okay, well, let's go to the room. I guess I will ask one question using my first privilege. Have you considered the interactions, or is this something you're going to consider in the future for your simulations, to include interactions between gas in these initial systems and interaction with the warm Jupiters? Is it difficult to include those in simulations? And do you think it is going to give realistic results like what you're showing?
Right. The reason I didn't include that is I'm saying like my personal belief. The worm Jupiters, they begin with somewhat compact system, and likely just like super Earth, some convergent dismigration. So if I can show that with the observed population, I trace back to the initial condition, and I get some separation that is on the verge of the dynamic instability, then it's an evidence of this migration. So that's why I didn't include that. I don't want to assume it already. I want to see, okay, our data is telling us, it's all compact system. So there must be some energy distribution mechanism, and it's likely to be the convergent migration. So yeah, I think this tells us the compactness of the system, and 4.34 is close to the dynamic instability. That's why warm Jupiter systems might be compact with the protection of disk. They are stable, and when the disk dissipates, they get unstable and becomes a population we observe. So that might be a story that we can sort of infer out of this result. Thanks.
What's the mechanism that the spin axis is aligned with the orbital axis?
What is so we have you have the star form, and it spins, so there's a disk. So it's like the angular momentum is conserved. You are spinning a pizza, you have the star in the middle, which spin like this, and then you spin out the material, you form a disk. So the disk is aligned with a star, and the planet formed in the disk, so their orbit are aligned with the star. So yeah.
I think what I had understood was that for young systems, you saw that they were not aligned. And then in older systems, they were.
I see.
So I'm trying
Yeah.
to understand, how do they get from this unaligned state to an aligned state?
Right. That's a good question. The plot I pick a little bit confusing.
It was the next.
Yeah. So even for the youngest ones, they're still like a giga year, and the difference you see here is mostly because of the effective temperature. So it shouldn't really show this axis. It's yeah.
So you don't think that's an evolution?
Some people may think of that, but like to me, it's like more of stellar type dominated. So we know those cool hosts are spin orbit aligned even for the younger ages ones.
Right.
So there's just some outliers that always there's some outliers.
So where are the hot, so there are no old hot hosts?
Right, cause like the star involved become giant, and yeah, all the way we could no longer do the real velocity.
No,
Yeah.
thank you. I didn't understand how it could evolve.
Right, yeah, that maybe I should pick a different plot. It's like one of the next clear
Maybe I
plot.
should pay closer attention.
No, yeah, that's totally solid, valid point.
So in your, then going to the modeling,
Uh-huh.
do you include parameters like the metallicity of the system or the total angular momentum of the system?
That's a great question. So the metallicity in a sense, we can turn that into the total mass, since it's a little bit iffy. We do see this mass metallicity positive correlation on giant planet occurrence rate. So higher metallicity whole stars tends to have more giant planets. So that's kind of the metallicity point. And then the angular momentum, we don't have the angular momentum, but we have sort of the angular momentum deficit, which is how non-circular the orbit are. And in our case, we have all the systems have the sigma E for a Rayleigh distribution. So they have 0.01, so very small eccentricity to begin with. So everything begins with somewhat circular, mutual coplanar setup.
Right. I was just curious, you mentioned you had a parameter was the total mass and another parameter was
Mutual separation.
the separation.
Yeah.
But I was curious, do you get a different result if you have your massive, the more massive component is very near and everything else is small, or the very massive component is far?
Right. That's a great question. It's all if I include that in the simulation base or not, right? So I for this set, I shuffle the masses of the planet, since I don't have a strong belief on that it should be ordering or not. But yeah, that's like the model has full potentials, like whatever you fit into that, and we find that whether it can be, whether the data tells us any preference on like some older massness.
So do you find any of these parameters are insignificant?
I haven't really tried to do really high dimensional since I still want to, I'm still like trying to hang out with the neural network and learning what it can do, what it cannot. I really fear to get a hallucination inference.
Right, but in theory, you could give it all sorts of parameters and
Exactly.
and it would say this parameter isn't important.
Yeah, exactly. Yeah, it can do all of those. Yeah, I just draw something out of my n-body simulation pool. I do the inference, it works or not. It can always give an inference, but then it's me like believing it or not. But like, yeah, there are definitely like all sorts of dynamical patterns can be explored out of this.
Yeah, maybe one last question. So as we continue to learn more and discover new systems, is the idea that with new improved observations and new discoveries, will these parameters and discoveries, do they go into like helping like the data, the training data set? Is that the idea? So that'll like these new observations will then help the work that goes into this modern simulation-based inference.
Right. That's a great question. So the more data we get, then the more robust the mass eccentricity space distribution we have. So it's always helpful, but we need to be careful on why those data are being taken, how are they being taken. So it's all the observation bias we need to consider in future once the sample size is getting larger. So far, we only consider the really rudimental one, which is a transit probability, and what is most likely to detect planet, what are the most likely to detect worm drifters, and assume they've been followed up, and that's why we get this population. So yeah, definitely a lot more to consider, and it's could be a quite complicated problem by the end.
Great, cool. Thanks, DJ, for this Q&A. Thanks, everyone. Thanks. We're going to have lunch on the night. Welcome, if you're free, feel free to join us. So